Okay, so in this next video, we are just going to review or see for the first time expressions or conditions that conductors in an electrostatic equilibrium mean. So the first thing to notice is we're talking about conductors. Remember, conductors are characterized by the fact that the electrons can move freely. And so that is one of the differences that you will have compared to a conductor and an insulator. Now, what we're looking at is we are not really looking at the conductors while the charges are moving around, but we want to know what would be sort of the situation once the charges moved around and then they reached a place where they were happy, and so that conductor was in equilibrium. So the electrostatic equilibrium implies that the charges are at rest, they're not going to move anymore, and they're in equilibrium, and there's no reason for them to move after this. So what happens is when we have this situation, there's a series of observations that we make that we want to remember because it's going to help us answer questions. The first one is that all the charge in the conductor, if it has an excess charge, will be on the surface of the conductor. Related to this, because all the charge is on the surface, the electric field inside the conductor has to be equal to 0. Next, we will find that the electric field is perpendicular to the surface of the conductor. And finally, the magnitude of the electric field at the surface is going to be sigma over epsilon naught. So let's go through and look at it individually. So basically, why does the charge have to reside on the surface? And when we say this, we mean excess charge. If the conductor has an excess charge, it has a charge of plus 2 nanocoulombs or minus 3 nanocoulombs, where is that charge going to be? So what happens is because of the mutual repulsion between like charges, they will tend to want to get away from each other. And what happens is the furthest away that they can get from each other is till when they get to the surface. Once the excess charge is accumulated on the surface, it really can't distribute itself any differently based on the fact that the repulsion kind of brought it to that point. And so that really helps us understand why the charge has to be on the surface. It gets away from the like charges as much as it can, and that's what makes it arrange itself on the surface. Now, as a consequence of that, the electric field inside the conductor has to be 0. So in this picture, we had a conductor. We see that all the charges are on its surface. So we wanted to use Gauss's law to figure out the electric field inside the conductor. So we chose this purple right here, this purple Gaussian surface within the conductor, and that's how we're going to find the electric field. But when we look at the right-hand side of Gauss's law and we say, hey, how much charge is inside that purple circle? And we say, nothing. So there's no charge enclosed, and so we are left with E dot dA is equal to 0. A is not equal to 0, which means that the electric field has to be 0. So the fact that all the charge goes on the surface follows up with the fact that the electric field inside the conductor has to be 0. Now, why does the electric field have to be perpendicular to the surface? So we imagine here's the electric field, it's perpendicular to the surface. Let's ask ourselves, what would happen if it wasn't? So that in this case, this electric field has a component parallel to the surface and perpendicular to the surface. This parallel electric field would exert a force on the charges on the surface that would be parallel to the surface, it would make the charges move along the surface. But we just got done saying we were talking about conductors in electrostatic equilibrium. So this cannot happen if we're in equilibrium. So we basically were able to show that the field has to be perpendicular by imagining what would happen if it was not perpendicular. We would come up with a situation that would imply that the conductor was not in equilibrium. So it's got to be perpendicular. Finally, the magnitude of the electric field at the surface has to be equal to sigma over epsilon naught. We use Gauss's law. This is similar to the sheet of charge that we did in a previous video, except now we made it a cylindrical box, and the only contributor to this is the top of this box, because on the sides the electric field would be 0, on the bottom the electric field is 0, so we only have a contributor on the top to the total integral here. And so the electric field and the area vector, you can see, are parallel to each other. The electric field's going to be constant. And the E times A. And if we divide by A, we get Q enclosed over the area over epsilon naught. Q over area is sigma, and we find that our electric field is sigma over epsilon naught. So the difference between this and the charge sheet for the insulator was that that had the electric field going this way, and it contributed another factor to the electric field, but not in the conductor because of the fact the field inside is 0. Okay, so what happens when we put all this stuff together? Some of these examples that you probably had in homework, and like we see in this picture, putting it all together can be challenging, but once you do it, it makes a lot of sense. So in this case, we have a conducting shell that has a cavity. So the yellow stuff is the conductor. So anything in yellow is inside a conductor, but then this is the cavity right here, the white thing, that's the cavity. That doesn't actually count as being inside the conductor because it's not conducting material. So what we've done is we've placed this point charge inside the cavity of the conductor, and we know that that's going to create an electric field that goes out away from it. But we also know that when it gets into the conductor, that field has to go to 0. So what has to happen is, well, we can look at it from 2 ways. We could think of the conductor setting up an electric field in the opposite direction to just cancel it out. But we can also look at it from the point of view of if I applied Gauss's law using this purple Gaussian surface, I would need to find total charge enclosed equal to 0, which means this minus sign means that negative charge has to accumulate on that inner surface of the conducting cavity so that it exactly equals out the positive charge that's in the cavity. So the negative charge is minus Q, because then minus Q plus Q equals 0. So right here we have minus Q. Now, what happens then? Okay, well, maybe the conductor had a total charge of something, like whatever it is, 3 microcoulombs, whatever. When the negative charges went in here, that left an excess positive charge on the surface that would be equal to the charge of the conductor plus this positive. This positive charge was added to the charge of the conductor because of the migration of the electrons. And so the total positive charge on the conductor increases from, well, originally the conductor had a charge of 3 microcoulombs, but 1 microcoulomb of electrons went to the inside of the cavity, which increased overall the positive charge on the surface by that same magnitude. We're going to look at an example that hopefully will make a little more sense when we put it all together. Okay, so let's look at some examples. Okay, a solid conducting sphere is placed in a uniform electric field. With regard to the electric field on the sphere's interior, which statement is correct? Well, we don't make up rules or observations to just block them out, so there has to be no electric field on the interior of the conducting sphere. What would have to happen is if I had an electric field, here's my sphere, here's my electric field, what would happen in the conductor is that charges would redistribute themselves in the conductor so that the total electric field inside the conductor would be 0. So you'd have that redistribution of charge that creates its own little electric field, but this electric field does pass through the conductor, and so the sum of those two have to add up to be 0. Okay, here is another example, kind of like that first picture I showed you where we were a little bit more vague, because now we have a conducting spherical shell with an inner radius A, outer radius B. So again, the yellow is the conductor. It has a total charge of minus 3Q. And here's the cavity. And we're going to be asked for some different questions. So for here we say, in the region between A and B, what would be true about the electric field? So once again, remember that we have this positive charge that was placed in the cavity created an electric field that was coming out away from it. But within the conductor, the electric field is 0. And we'll look in a moment why that has to be true. But we know if we're in the conductor, electric field is 0. So the answer to that question is just based on the rules we know about a conductor. But now we're going to get into more details. If the electric field here is 0, how does charge arrange itself in the conductor? So what happened is if this was plus Q, then we have to have negative charge has to build up on this inner surface to keep the total electric field 0 within the conductor. So the negative charge that's placed on this surface is minus Q. And then, because the total charge that the conductor had was minus 3Q, we've put minus Q on the inside. So the remaining negative charge has to go on the surface, which would be minus 2Q. And so that's what we make. So when you look at then the inner surface plus the outer surface, these things add up to be minus 3Q. So it all works out. Hopefully this helps. Have any questions? Shoot me an email because we're going to have that LO assessment on Monday.